Using Morse circle, we need to determine the principal stress and the maximum in plane shear stress and average normal stress at the point illustrated in the figure. And we also need to specify the orientation of the element in each case. So we can see from the original state of stress that we were given, the sigma x is 15 kilopounds per square inch, positive value because it's tensile, and the shear stress is minus 5 kilopounds per square inch. Alright, we are going to be using Morse circles, so first of all we have to construct it. Let's draw the plane over which the Morse circle is going to be drawn, and we are going to first locate the center of the circle, which is given by the average stress. So sigma x here is 15 kilopounds per square inch, sigma y is 0. So we find that the center, or the average stress rather, is 7.5 kilopounds per square inch. That is just a normal stress, so we have to locate it along the horizontal axis at a location 7.5. The next thing that we are going to calculate is the radius of the circle, which is given by this equation here. Again, sigma x is 15, sigma y is 0, and tau xy is minus 5, but in this case, because it's a square, the negative sign does not matter. We end up with a radius of 9 kilopounds per square inch. So we have the radius equal to 9. And now we can draw the circle. We are going to be locating the state of stress represented in this square here. So first look at the positive x face of that square, and that represents the axial stress along x as well as the shear stress. So we have coordinates plus 15 minus 5. So the x point is located at this location. Now the other side of the diameter is going to give us the perpendicular, the values of the stresses at the perpendicular plane, which is 0 normal stress. So it's basically where the Morse circle coincides with the vertical axis, and then 5 as the shear stress. So we have represented that state of stress on Morse circle. We want to look at principal stresses. So the maximum principal stress would be given by the intersection of the Morse circle with the horizontal axis at this point. So that's sigma 1, which is just the center plus the radius. So we obtain 16.5 kilopounds per square inch. And the minimum principal stress would be at the other side of the diameter. So sigma 2 is the center minus the radius, or minus 1.5 kilopounds per square inch. You can think of the maximum principal stress as the maximum normal tensile stress, and the minimum principal stress as the highest normal compressive stress. The orientation of those principal stresses, well, we start from point X, or basically from the horizontal, and then we start rotating from X until we arrive at the diameter where sigma 1 is. So it's basically this angle here. Remember that on Morse circle, the angle is represented by the double angle, so that's 2 theta p1. And we can find this angle through the tangent of the ratio of this distance, which is 5, divided by this distance, which is 15 minus 7.5. So therefore, 2 theta p1 is the arctange of 5 divided by 7.5, or 33.69 degrees, which divided by 2 end up with 16.84 degrees. That would be a negative value because the rotation is clockwise. To go from X to sigma 1, we have to rotate clockwise. So in reality, theta P1 would be minus 16.84 degrees. And this is what we have represented here. So 16.84 degrees clockwise from X, we have the orientation of principal stresses that are maximum, 16.5 kilopounds per square inch, and the perpendicular plane will give us the direction of minimum principal stresses, which are 1.5 kilopounds per square inch in compression. We are going to do the same thing for the maximum in-plane shear stress. Remember, the maximum plane shear stress would be given by the highest value along these ordinates, so it's basically at the top and bottom of the circle as given by that line, the orange line. And we find the value is actually just the radius, which is 9 kilopounds per square inch. Now, to find out the orientation given by the plane with a maximum shear stress, we start again from the horizontal or point X and start rotating towards that plane of maximum shear stress. In this case, we are rotating counterclockwise. Mohr circle will give us always the double angle, so 2 theta s. So if we find out the tangent of this angle, which is the tangent of this distance here, which is 15 minus 7.5 divided by this distance here, which is 5, just given by that triangle, we find that 2 theta s is 56.31, which divided by 2 is 28.15 degrees. The rotation node that is counterclockwise, going from X to the plane of maximum shear stress, so that means it's going to be theta s is going to be positive, and that's the representation of the inclination of maximum shear stresses. So as we rotate 28.15 counterclockwise from X, we find out the inclination of the shear stresses that are maximum. And note that along those planes we have normal stresses, and the value of the normal stresses are those given by the average stress or the coordinates of the center of the circle, which is 7.5 kilopounds per square inch.